Hello, everybody. This is Kamal Choudhary from NIST. I'm a contractor research scientist at NIST right now. And I'm going to talk about our JARVIS project, which is a part of Materials Genome Initiative at NIST. Before I go in the details, I would like to thank all the collaborators for this work in NIST and as well as outside several university and national lab, especially the contributions from Francesca Tevezza, Kevin Garrity, and other team members. So I'm pretty sure most of you are familiar with this, but let me go through this in very briefly. What is material science? Mainly is this PS-PP relationship. And although it's a key mantra or formula in this material science, it depends on different length and time scale, right? It may be microstructure, it can be atomic structure, and so on. In the present discussion, we'll be mainly focusing on the atomic structure or electronic structure. So computationally, a structure can be defined such as lattice constant, parameter, basis vector, and you can calculate these properties using classical molecular dynamics or density functional theory and so on. So in Materials Genome Initiative, encourages this idea of integrating several methods and experiments and data analytics tools to accelerate material design. So that is a basic motivation behind this work. So I don't need to convince you why we need open material databases, but definitely some of the key advantages or challenges are to accelerate computational and experimental methods and discover new materials or characterize new materials, automated literature searches, hopefully finding new physical equations, efficient categorization of materials. At NIST, we care about uncertainty quantification, reproducibility, and although I think in Optimat and other workshop, they mainly focus on atomic structure data. There can be different type of material structure data. It can be from crystal structure, from molecules, for proteins, experimental band structure, images, spectra, and so on. So idea behind Material Genome Initiative, which was initiated by former US President Barack Obama, was to actually integrate all these different methods and tools for accelerated material design. So JARVIS is a part of, again, NIST chapter of Material Genome Initiative. So as I said, this infrastructure, the idea is to, for example, choose a performance metric. Suppose you want to design a solar cell material. This is your solar cell efficiency will be a metric. Then you can choose a appropriate method. It can be DFT or any other machine learning method. And these are the 6 main components of JARVIS infrastructure. And hopefully by the end of this whole process, you'll have optimized material. So right now we have some of the main components are classical force fields, density functional theory, beyond density functional theory methods, machine learning, and open access tools. This is mainly provided at the jarvis.nist.gov, and this is our GitHub page. So it has several components, as I mentioned, density functional theory, scanning tunneling, microscopy, tools, so on. Right now, we have around 40,000 bulk 3D structures, around 1,000 2D materials, 110 classical force field, and more than 1 million calculator properties. And all these properties and etc. are calculated and stored at NIST computers. So we started with evaluation of classical force field to guide a user what kind of force fields to choose based on the density functional theory data. Then we discovered several 2D materials based on the lattice parameter criteria and the error in PBE and experimental lattice constant. We saw that there's a huge error in the band gap prediction of several PBE methods. So we used this meta-GGA TB MBJ method to solve that some of the problem to a certain extent. And we developed an elastic constant data set for around 15,000 materials using van der Waals functional. We developed a spin orbit spillage criteria to discover new topological materials. It can be magnetic, non-magnetic, 2D, 3D, or insulating or semi-metallic. And then we developed this machine learning classical force field inspired descriptors, which gives a universal fingerprint of whether it's 3D or 2D material. We applied this for finding several solar cell materials and finding converged K points and the cutoff for DFT calculations, infrared piezoelectric dielectric materials, 2D as well as magnetic and non-magnetic materials. And we applied several transfer learning approaches. And right now we are expanding more and more for several properties such as electric field gradients for nuclear magnetic resonance and are quadruple resonance, for 2D vendor wall structure, electric, so on. And this is one of the projects. And impact wise, although we started around 2017, we see around today, but it's definitely something just like this. And according to the Google Analytics, we have visitors mainly from US and India and China. And our tools are, you can see, it's downloaded at several thousands. And we have several research publications to support our work. We organize two major workshops, artificial intelligence from material science, aka AIMS, and quantum materials from matters in material science. Unfortunately, though both of them are canceled this year due to the COVID-19. And we are getting nice feedbacks from the community. We also provide all the data in Figshare, and which I think is a very nice resource, and we are getting nice response there too. So Jarvis tools has three main components: automation of several methods such as density functional theory, molecular dynamics, machine learning, linearization, calfate processes, and ODFR, like finite element method, are already developing. This is the automation part. After we automate, we post-process this data. It can be either discrete data, such as band gap formation energy, can be continuous data, such as dielectric function, density of states, and so on. It can be image data, such as scanning tunneling microscopy. And then we convert into a JSON or XML or other format. And for most of our method in our tool, we have a to-dict and from-dict method. And I would love to have a feedback from Optimate community for their ontology of how they define different schema. And this is one of the reasons I'm very excited to join this workshop. And after we do this post-processing, we disseminate using several publications or different web apps based on complete JavaScript or just Flask app, and then several Jupyter notebooks or Google Colab notebooks, and several REST API. Our REST API is still in the kind of progress, but we have provided all the input file, output file, tools in Figshare, Google Drive, and so on. So a few examples why we are excited about this is because our database and tools are linked through this Colab and Figshare. So basically, you don't need to even install any software on your computer or download database. You can just have a Gmail account, and the Colab will be able to basically have you post-processing or a machine learning application just on the, you can do the even phone also. And we use several continuous integration right now on code, but we would like to do that with the database. I think this is one of the components we are missing right now. So how to have a continuous integration on the database and their sanity of the database. And the tool wise, here's a very brief snapshot. So it's very similar to ASC and PyMedGen and other tools there, but we try to have minimal dependencies. So my personal experience is that if you have a lot of dependencies on your tool set, it may break down very easily, not for you maybe, but for other users who are not very experienced with these Python tools. So we try to keep the dependency really, really very low. And as I said, it's linked to Figshare. So you can download the whole, for example, 40,000 materials as a one JSON big giant array, and you can do post-processing using Pandas data frame and so on. As I said, and we are also having a REST API with the NIST MDCS instance. So this is still in the work in progress, but it will be up there soon. So once we have these tools, and we have around thousands of cores from NIST, we get three major databases: JARVIS-DFT, JARVIS-FF, and JARVIS Machine Learning. In JARVIS-DFT, unlike other databases such as, which mainly uses PBE functional, we are trying to go beyond and use something like op-B88 van der Waals, TB-MBJ, GW, spin orbit coupling, dynamic mean field theory, and so on. And we are adding several protocols, such as one of the challenges in other databases, they don't converge, for example, not necessarily converge the K points and cutoff for each of the materials. So we have a convergence protocol for K points cutoff. We also are developing a one-year function protocol in DFT. And this data is compared to experiments to have uncertainty quantification or error analysis. This is the JARVIS-DFT part, around 40,000 3D and 2D materials. We also have a JARVIS-FF, which is a classical force field data set, around 15,000 materials and 110 force field. Right now, it's basically like old EAM and meme type potential, but we are trying to add other machine learning potential there as well. In JARVIS-ML, it's a machine learning descriptor and target and model data set. So after we use your descriptor and data, you can easily just take it in your scikit-learn or I don't know, Keras kind of framework easily from Figshare and start doing machine learning. It's a very well curated data set. And we have converted, for example, major crystal structure databases such as crystallographic open data set, our own JARVIS-DFT, Materials Project, eFlow, and so on, and convert it into a descriptor set so that you can just take that and start doing machine learning on our descriptor set and their data. So this is still in work in progress, but we have done that internally, and we have trained several models, machine learning model, whether it's classification or regression or clustering. And we at NIST, we are very interested in uncertainty quantification. So we are working on several uncertainty quantification from machine learning tools. This is a snapshot of JARVIS-FF. Again, the idea is you can choose an appropriate force field from molecular dynamic simulations. So you can go to the JARVIS-FF website, which is hosted on CTCMS. And then you can choose, for example, nickel aluminum, maybe one system. And then you can find there may be like 30 different potentials. So which one should I choose for my simulation? So you can compare this automated data set, which is LAMMPS-based calculation data set for convex hull and phonons and elastic modulus. And you can convert, for example, DFT versus the classical force field convex hull. And for some of the phases, you can see the convex hull is not similar in DFT. So it should not be, it would be difficult to simulate in molecular dynamic simulation. And right now it's mainly in EAM kind of potential. So as I said, you can take a look on the DFT on the left-hand side, and the right-hand side is the classical force field EAM potential. Some of the phases which are there in DFT stable are not stable in the LAMMPS-based classical force field. So it indicates that this potential may not be suitable to that kind of molecular dynamic simulations. Same as in the bulk and shear modulus data, some force field may be designed for energy, but not for bulk modulus. So it may be giving error. So this kind of error analysis or uncertainty analysis will give the users, hopefully, some guideline which potential to choose. This is Jarvis density functional theory for functional material design. And this is again the CTCMS website. So if you go to the website again and suppose search boron nitride, you can find a full page for each material. So around 14,000 web pages are dangling there. So which is all after the calculation of DFT tool workflow, it generates a web page. So right now we have several properties for 40,000 materials, such as crystal structure and formation energy, band gap kind of traditional kind of thing, K point and cutoff converged, and then solar cell efficiency, topological spillage for topological materials, 1 year tight binding Hamiltonian, which is still, we are working a paper on it, dielectric, piezoelectric, thermoelectric, and exfoliation energy, phonons using density functional perturbation theory and finite difference method for 5,000 and 15,000 materials respectively, infrared and Raman activity, electric field gradient, magnetic moment, scanning tunneling microscopy, 2D heterostructure, work function, and so on. Here's an example of all this data set. So for example, solar cell discovery materials. So we take the dielectric function from the MBJ and calculate something called spectroscopy limited maximum efficiency, first originally developed by Alex Zunger. And then we, for around 15,000 materials, we calculate this SLME. And for handful data, you'd be surprised there's no well-curated data set for experimental solar cell efficiency. We found that the TBMBA solar cell efficiency around 5%. So after that, we did screening, for example, give me all the materials with more than 10% efficiency and less than 1 ME effective mass. And how many of them could be layered 2D, 1D, 0D, and 3D material, and so on. So such kind of analysis, you can find details in our paper. And also the chemical analysis, what kind of elements are supposed to show up in the periodic table for high solar cell efficiency materials. So this was solar cell. Let me go through briefly on topological materials. So these are a special class of materials apart from metal, insulator, and semiconductor. These materials are supposed can have, for example, in insulating case, both insulating and metallic phase. So here's example of regular insulator. We have conduction band is red and the valence band is blue, but in topological insulator, they are characterized by something called band inversion. This band inversion phenomena can be captured by something called spin orbit spillage, which was proposed in 2014 by David Vanderbilt group. And so spillage is similar to the idea of spilling something. So how much extra you get due to the inclusion of spin orbit coupling in your wave functions. And you can find detail again in these papers, but the idea is if a material has spillage, then it should be a non-zero spillage, then it should be topologically non-trivial. And the wonder of this technique is it can be worked for magnetic, non-magnetic, and insulating and metallic material. Right now, we have characterized at least 3,000 3D and 100 2D high spillage materials. After we do this spillage analysis, and again, this is an example of spillage. So this band structure with and false spin orbit coupling of bismuth selenide. You can see in the selenium P state, it should be all occupied in the green band and it should be all unoccupied. But as you turn on spin orbit coupling, there's a band inversion. That means there's a red character in the valence band and green character in the conduction band, and this will give you high spillage. So after this spillage screening, we do several one-year kind of analysis using VAST, and we calculate something like bulk and surface band structure for 3D and 2D materials to find Dirac cones. And it can be worked for magnetic insulating phase as well as for semi-metallic phases. So in machine learning, the idea is to accelerate materials discovery using machine learning methods. And we have trained several models and developed a Flask app, which can predict the properties using this descriptor and data set. So right now we have traditional properties such as formation energy and band gap, but we are also adding something like piezoelectric constant, magnetic moment, and so on. So for any machine learning model, you need descriptor and data set. So we have found that this descriptor set called classical force-field inspired descriptor, CFID, has around 1,500 descriptor for each material, which consists of a radial distribution function, angle distribution function, dihedral distribution function, and charge distribution around the core of the material, and chemical properties such as boiling point and melting point, so on, very well known in this community. And we can get around 1,500 descriptor for each material in this. And this is the crystal space featureization. We also are working on a image STM image kind of image curation data set. And then we have trained several classification and regression models. So we store and distribute the models, the model parameters, the tools that is used, and the data set which is used for the machine learning process. As example is finding 2D materials using machine learning. So these are some of the models that we have trained. For example, exfoliation energy, regression model, and then we also have a classification model for band gap, whether you want to know whether a material is metallic or not. You can just you can see around this area under curve should be 1 for a perfect model, but it's around 95, which is pretty good. So using this two combined model, first we apply the classification model and then the exfoliation energy regression model to find several 2D candidate materials using machine learning, and then we verified using density functional theory that they are actually exfoliable. The previous example was accelerating the density functional theory kind of calculation. It can be also used to accelerate experiments. So one of the idea is the scanning tunneling microscopy. So for many 2D materials in our data set, using this Chertsov-Hamann approach, we calculate the scanning tunneling microscopy images. And one of the problems we try to solve is what kind of Bravais lattice the 2D materials are. So you can take the several like hexagonal, rectangular, and oblique kind of 2D material and do a Fourier transform of it to like, for example, the figure D is a Fourier transform, which you can see is a hexagon. But if you see, for example, P, it's not that easy to distinguish whether it's an oblique structure or not. So manually, it can be very challenging to characterize this process. So why not train a machine learning model for this? So we trained a classification model using deep neural network, and then we found around 90% accuracy, overall accuracy, and you can see the confusion matrix here, that it can more or less highly accurately classify this Bravais lattice based on the image. So we got a little excited and tried this model on actual experimental images that we got from Google Images, literally downloaded it and applied this model, which was working for most of the cases. So again, although these are trained on the perfect model, perfect data, it can, with some kind of augmentation technique, you can train on the noisy data set too. And similar thing for density functional perturbation theory kind of data set. We did several screening from finding infrared material and piezoelectric, and then that can be used for guiding machine learning process. For example, finding high piezoelectric materials, high dielectric constant materials. we found that we can train machine learning model for infrared activity mode and the bond effective charge and so on. So after this main repositories, we have derived apps too. So this repository called JARVIS heterostructure, and it uses Zur algorithm and Anderson rule for finding 2D heterostructures. And I think around 700 out of 700 materials, you can think of the different combination of this 2D heterostructure. There can be around 2 million possible heterostructure, which is almost like infinite to characterize experimentally. So we developed an app using Flask. You can select 2D material, and it will tell you what kind of band alignment would be based on plain DFT. So this is one of the derived app. Another is Jarvis one-year tight binding Hamiltonian tool. So this is still not published yet, but we have around 70, 78, 71 3D and 2D one-year tight binding Hamiltonian using VASP. So you have developed a workflow for one-yearization. And then we have developed this app that can solve the key point. Based on key point, it can solve the band structure and density of states. And we're going to add some other tools such as surface band structure and so on. This is all based on the Flask apps. So in a nutshell, I was really briefly give you an interview of the NIST JARVIS dataset using different simulation method, not just DFT, but other machine learning and other methods, which are all integrated and based on MGI philosophy. So right now we are giving all metadata on fixture, but we are planning to give really thousands of input and output file for VASP and LAMPS and so on. And this is a well-curated data set that you can easily plug in a machine learning kind of framework. So we are looking forward to integrate with other data sets, such as I heard some really wonderful talks on Optimad and Nomad and so on. So we'll be very delighted to integrate, and the idea is again to serve the community. So in any way that is possible, we'll be happy to collaborate. And we want to expand these properties, and also NIST is a primarily experimental facility. So we are trying to integrate some experimental data as well. So, and we are doing something called Beyond DFT with Rutgers University Group to go beyond density functional theory methods using DMFT and so on, developing graphical convolution network and finite element simulation techniques. Another thing would be developing a cloud-based service that can reach, right now we already are hosting the data which is calculated, but what if some of the users from our developing countries want to their own calculations? So based on this tool and data set, we hopefully in future we'll be able to develop a cloud service so that they can do calculation there. And if you are wondering about this name, yes, this name is inspired from the movie Iron Man, which is one of my favorites. And with that, I'd like to thank you for your time, and really thankful to the organizers of this wonderful workshop. And I'm looking forward to the discussion. And yeah, with that, I'd like to stop here.